Hello and welcome to the Quick Solutions All India AIATS Test Series JEE Advanced 2021 Test 2A Paper 2 Physics. Let's go to question number 1. Question 1 says a particle is projected in vertical plane with minimum possible speed to just cross the fixed smooth cylinder of radius r as shown. The value of V0 is. The question is obviously from projectile motion, and the point to note here is that the cylinder is fixed and its surface is smooth. And in that case, what is the minimum speed with which the particle should be projected so that it can cross this cylinder? Well, here we can conserve mechanical energy, and the point is that once the particle lands on the cylinder, right, so its tangential velocity will not be affected, right, due to collision. Well, here the cylinder is smooth, and that's a key point, which means that we can simply conserve mechanical energy to find the minimum speed. And if we do that, we just have to take the projectile to the top of the cylinder, and even if it is reaching the top of the cylinder with speed very close to zero, it will be able to cross over the cylinder. So which means we can write half mv0 square, as I said, by conserving mechanical energy, is equal to mg into 2r. So basically we are just taking the projectile to reach the top of the cylinder, and this gives us the value of V0 as under root 4 rg, which is matching with option D. So option D is correct for question number 1. Let's now go to question number 2. Question 2 says a particle attached at one end of an ideal string of length 5 meter is released from the position shown in figure. If collision between particle and smooth surface is perfectly inelastic, then time interval during which the particle moves on the flat surface till it leaves the surface again is, and g is 10 meter per second square. This is the figure that's given to us. This is the initial position. The length of string is 5 meter and the floor is at a distance of 4 meter from the fixed end of the string, and for the collision value of E is 0. So we have to find the time interval during which particle moves on the flat surface before it leaves the surface. Well, we can apply concepts of conservation of mechanical energy to find the speed of the particle before hitting the surface, and its collision with the surface will be oblique collision and surface is smooth. So the component normal to the surface will become 0 and the component of velocity parallel to the surface will remain intact till it leaves the surface when the string becomes taut again. Okay, so just to find the speed, let's say the trajectory that the particle follows before it hits the surface is something like this. Okay, if it had not hit the surface, it would have come all the way here, but before it comes, it hits the surface. And let's say the speed here is v1. So the expression for v1 we can get very easily by writing half m v1 square, conserving mechanical energy, is equal to mg into 4 meter. Now let's strike off m, and value of v1 we are getting is equal to under root of 8g, and if you put the value of g as 10 meter per second square, it is under root of 80 meter per second, which means it is 4 root 5 meter per second. So that's the velocity just before hitting the surface, and this is v1. Now at this point, this distance is 5 meter because the particle is moving along arc of radius 5 meter, which is the length of the string. And so we have a right angle triangle whose one side is 4 meter, the hypotenuse is 5 meter. The other side will obviously be 3 meter by applying the Pythagoras theorem. And this is the velocity v1 before hitting the surface. Let's resolve it into its horizontal and vertical components. We are interested in the horizontal component. Now, if this angle is theta, we can see that this angle is also theta, and which means the tangential component of v1, or we can say v1t, or the horizontal component also, is basically v1 sine theta, and that means its value is 4 root 5 meter per second, which is V1 into sine theta. And if we have taken this angle as theta, so sine theta is 4 by 5. So this into 4 by 5, or simply 16 by root 5 meter per second is the horizontal component. And we can see that the string becomes slack thereafter, and the particle goes like this. And once it travels another 3 meter, and then the string will become taut, because the string will be fully stretched at that time, and then it will leave contact with the floor. So that means the total horizontal displacement after collision till it leaves the surface is 3 meter plus 3 meter, that means 6 meter. And this 6 meter, the particle will travel with a uniform velocity of 16 by root 5 meter per second. So the time will then be equal to the distance it's traveling, 6 meter divided by 16 by root 5, and we can write it as again 3 by 8. Let's put 1 root 5 in the denominator, and then the numerator you have 5. So this is giving us 15 by 8 root 5 seconds, right? This is equal to 15 by 8 root 5 second. And if we look at the options, it is matching with option D. So option D is correct for question 2. Let's go to the next question now. Question 3 says a particle of mass m is attached at the circumference of a uniform disk of same mass. The arrangement is in state of pure rolling on rough horizontal surface as shown. If at the given moment of time, center of disk has acceleration a0 just after release, then we can conclude about n, normal reaction on the disk from ground, and direction of frictional force on disk. Let's draw free body diagram of this system, and we have forces. Well, the center of mass is exactly midway between these 2 points. So we have 2 mg acting through the center of mass. We can call this point C. There's normal reaction acting through this point, through the point of contact, and there is also, it's a friction. Well, friction could be towards left or right. We can, let's wait before we decide which way the friction is going to act. Now, if I take torque about the point of contact of this force 2 mg, the torque of friction and torque of normal reaction is obviously 0. So we get a positive torque in the clockwise sense about the point of contact, which actually means that the body will have angular acceleration in the clockwise sense. Okay, and the center of mass will have initial acceleration in this direction. That means I join center of mass with the point of contact and normal to that. If this length is L, which we can find if we want, this will be alpha times L. That's the initial acceleration of center of mass. So we can see that the center of mass has acceleration which has a vertically downward component and a horizontal component towards right. Now the center of mass has horizontal component towards right, which clearly means that the friction has to be acting towards right for this to happen, because there is no other horizontal force on the system. So that means friction is acting towards right, which is what we call the forward direction. It's going to move towards right. And since the center of mass has a vertically downward acceleration also, it clearly means that 2 mg is greater than the normal reaction. Okay. In fact, 2 mg minus n will be 2m into acceleration of center of mass in the vertically downward direction. So with all this, we can now conclude that n is less than 2 mg and the friction is acting in the forward direction. Now if you look at the options, option C is matching with this. Let's go to the next question now. Question 4 says 4 identical point masses m are kept symmetrically on a circle of radius r as shown. If W1 is the work done in moving mass 1 till infinite very slowly from this position, then gravitational potential energy V of this configuration of masses 1, 2, 3 and 4 shown in figure is equal to. Well, the gravitational potential energy we can find by using the formula, because it's a system of 4 particles. So we have to consider every pair of particles, and for one pair the formula is minus g m1 m2 by r. So if I take 1 and 2, then it is minus g m square, and the distance between 1 and 2 will be r root 2. Similarly for 2 and 3, similarly for 3 and 4, and 4 and 1. So that means we have 4 terms like this, so we multiply it by 4, and then there is gravitational potential energy between 1 and 3 and between 4 and 2. So that is 2 times minus g m square by 2r, right? So essentially, I am repeating, essentially there will be 6 pairs out of 4 particles. 4 pairs are at separation of r root 2 from each other, and the 2 pairs are at a separation of 2r. So this is the total gravitational potential energy of the system. And well, we have to express this in terms of W1, where W1 is the work done in moving mass 1 to infinity very slowly from this position, right? So to calculate W1, what we do is we find gravitational potential energy, let's call it U2, when 1 has been taken to infinity and other 3 remain. Well, if other 3 remain, then we have only 3 pairs, and one pair is between 2 and 3, the other pair is between 4 and 3, and then one pair is between 4 and 2. So that means the gravitational potential energy in that case is going to be minus g m square by r root 2 into 2, because there are 2 pairs like this, and there is this minus g m square by 2r. Okay, now we can see that we can give it name ui, it is better. So we can see that ui is actually 2 times of u2, and the work done W1 is actually equal to change in potential energy of the system, right? So that means u2 minus ui, and as we just saw, u2 minus ui, u2 is half of ui, okay? So u2 minus ui is equal to u2 minus 2u2, or simply minus of u2, and so that means we can write u2 is simply minus w1, and this means ui, which is 2u2, is minus 2w1, and which means option D is correct for this question. Let's go to the next question now. Question 5 says a block of mass 1 kg is attached at lower end of an elastic string. Natural length L0 is 1 meter. Upper end of string is slowly pulled till the time block just leaves the contact. If at the time of leaving, point A on the string, which was originally at a distance 0.8 L0 from the mass, shifted by 0.2 L0 from its initial position as shown, then total work done by force in this process is, assume elongation in the string is uniform. And this is the diagram given, and these are the options that's been given to us. Well, so the final tension, because the block is just lifting, so the final value of F is simply equal to 10 Newton, right? 1G, and that is equal to 10 Newton. That's the final value of F. Now if we can consider any part of the string as a spring, okay? So now tension, we can consider that everywhere is 10 Newton, and if we consider this part, let's call this point B, part AB, which has original length 0.8 L0. If spring constant for this part is, let's say, K1, then we can see that if total elongation of the spring is delta L, okay, this is the total elongation of the string, that's what we have considered, then delta L into effective spring constant is equal to 10 Newton. That's what we have, right? In fact, it's given to us. The length of BA portion has increased by 0.2 L0. So what is the total elongation of the string? We can use the unitary method, right? So delta L will be then 0.2 L0. This is the stretch for 0.8 L0 into total length L0 divided by 0.8 L0. So this is by applying the unitary method, okay? And if we do that, the value of delta L is coming out to be L0 by 4. The value of L0 is given to us, that means this is 1 by 4 meter. And the total energy stored will be half K delta L square. So the energy stored is half K delta L square. Value of K is 10 divided by delta L, which is 1 by 4. So that's half K into delta L square, that's 1 by 16. And let's evaluate this. This is 4, it's 10 by 8, and in fact it is 5 by 4 joule. And if we look at the options, it's matching with option B. So option B is correct for question 5. Let's go to the next question now.